We saw how the electrical grid evolved from isolated DC system to interconnected AC power system and finally towards the smart grid. Today, we are going to answer a very important question. Why do we need a smart grid? Before we discuss smart grid technology, we must first understand the limitation of the existing or conventional power grid. Because unless we know the problem, we cannot appreciate the solution. Think about it. Suppose your mobile phone is working perfectly. Would you think of buying a new smartphone? Probably not. You only replace it when you start facing problems. For example, the battery drains quickly, it becomes slow, it hangs frequently, it doesn't support new application, or its camera quality is poor. Only then you decide that it's time to upgrade. Exactly the same thing happened with our electric power system. For almost 100 years, the conventional power grid has served humanity exceptionally well. It supplied electricity to industries, homes, hospitals, schools, railways, and commercial buildings. Without this power system, modern civilization would not have been possible. So, first of all, we should appreciate the conventional grid because it has successfully powered the world for decades. However, the world has changed dramatically. Today's electricity system is completely different from what it was 50 years ago. Today, we have electric vehicles, solar rooftops, wind farms, battery energy storage system, smart homes, artificial intelligence, Internet of Things, cloud computing, digital communication, and millions of electronic devices connected to the network. Now, let me ask you one question. Was the conventional grid originally designed for all these technologies? The answer is no. Large thermal power plants generated electricity. Consumers simply consume electricity. There was no rooftop solar system. There were no electric vehicles. There were no smart meters. There was no internet based communication. There was no artificial intelligence. Therefore, although the conventional grid is reliable, it cannot efficiently satisfy today's modern requirements. This is the primary reason behind the development of the smart grid technology. Now I want Now I want to all of you to think about one simple situation. Suppose your house has installed a 5 kilowatt rooftop solar plant. During the afternoon, your family is not at home. Very little electricity is being consumed. However, the solar panels are producing the significant amount of electrical energy. Now tell me, what should happen to this excess electricity? Should it be wasted or it should supplied back to the electricity grid? Obviously, the best solution is to send the surplus power back to the grid. But the conventional grid cannot efficiently handle this situation because it was designed for the one-way electricity flow. This is only one example. Throughout today's lecture, we will discuss many such limitations. So, by end of this lecture, you should be able to answer the following question. So, these are the learning outcomes of today's lecture. So, first one is the why is the conventional grids become inadequate? Why is the conventional grid becomes inadequate? Then the second question, what are the major technical problems of the existing grid? Technical problems of existing grid. Then third, What operational challenges do utilities face? Operational challenges. Then next, why is the conventional grid economically inefficient? Economically inefficient. Then next, how does it affect the environment? And the last one is, why are consumers dissatisfied with the existing electricity system? So, consumer dissatisfaction. So, if you can answer these six questions, then you have understood today's topic completely. Now, look carefully at this figure. Although there are many problems in the conventional grid, we can classify them into five broad categories. The first category is the technical problem. There are These are directly related to electrical engineering aspects such as transmission losses, power quality, voltage regulations, aging equipment, and one-way power flow. The second category is operational problem. This involve the daily operation of the power system, including manual monitoring, slow fault detection, limited automation, and lack of real-time information. The third category is economic problem. Every electrical utility wants to provide reliable electricity while keeping operational cost low. Unfortunately, manual operations, energy theft, billing errors, and frequent maintenance increases financial losses. The fourth category is environmental problems. Modern society is moving towards renewable energy and sustainable development. However, the conventional grid depends mainly on fossil fuels and struggles to integrate renewable energy sources. Finally, the fifth category is consumer related problem. Consumers today expect a transparency, real time information, quick fault restoration, online services, smart metering, and participation in energy management. Unfortunately, the traditional grids offer very limited consumer involvement. One important thing to remember is that these five categories are not independent, they are interconnected. Let us understand with a simple example. Suppose a transformer becomes old. Eventually, this is a technical problem. Eventually, it fails unexpectedly. Now, engineers must visit the location and repair it manually. This becomes an operational problem. Repair works require labor, then equipment and spare parts. Now it becomes economical problem. Because electricity supply is interrupted, diesel generators may be used as a backup. That increases pollution. Now it becomes an environmental problem. And finally, consumers experiences power failure and becomes dissatisfied. Now it becomes a consumer related problem. So one single technical problem can eventually affect every stakeholders in the electric power system. This is why the smart grid technology focuses on improving the entire ecosystem instead of solving only one problem. So far, we have understood that the drawbacks of the existing power grid can be classified into five categories. Now let us begin with the first category. What is technical problem? So technical problems are the physical and engineering limitations of the conventional electric network. These limitations reduce the efficiency, reliability, flexibility, and quality of power supplied to consumers. In this section, we will discuss six major technical problems. So, first one is the one-way electricity flow. One-way electricity flow. Then, second one is the high transmission and distribution losses. High transmission and distribution losses. Then, third one is the poor voltage regulation. Then, next one, poor uh, power quality issue. Power quality issue. Then, next one, frequent power outages. Frequent power outages. And last one, aging of equipment. Aging equipment. So let's start with the first one. Please look carefully at this figure. What do you observe? You can see a power plant on the one side and a house on the other. Between them, there is a single arrow pointing from the power plant towards the consumer. Notice something very important. There is no arrow in the reverse direction. This single arrow represents the working principle of the conventional grid. Electricity is generated at the generating station. It is transmitted through high voltage transmission lines. Then it passes through substation. Finally, it reaches our homes through the distribution network. So the electricity always flow from the utility to the consumer. The consumer only receives electricity. The consumer never sends electricity back to the grid. This was perfectly acceptable 40 or 50 years ago because consumers were only electricity users. But today's scenario is completely different. Today, many consumers have rooftop solar system, some industries have wind turbines, many buildings have battery energy storage systems. Electric vehicles are also becoming mobile energy storage units. These consumers not only consume electricity but also generate electricity. Such consumers are known as prosumers. So, a prosumer is a person who both produces and consumes electricity. Now, let me ask you a question. Suppose your house has 5 kilowatt rooftop solar system. At 1 pm in the afternoon, your family is not at home. The solar panels are producing 5 kilowatts, but your home is consuming only 1 kilowatt. So, what should happen to the remaining 4 kilowatt? Should it simply wasted? Of course not. Ideally, the surplus electricity should be exported back to the utility grid. However, the conventional grid was not designed for reverse power flow. Therefore, integrating rooftop solar becomes difficult. Exactly, the same problem occurs with the battery storage system and electric vehicles. In smart grid technology, this problem is solved by introducing two-way power flow. Consumers becomes active participants instead of passive electricity users. Then coming back to the next losses, high transmission and distribution losses. First, let me ask you one simple question. If a thermal power plant generates 100 megawatt of electric power, do consumers actually receive full 100 megawatt? The answer is no. Some portion of the electrical energy is lost before it reaches consumers. Why? Because electricity has to travel through hundreds of kilometers of conductors. Every conductor has electrical resistance. According to Joule's law, power loss is equal to I square into R. As current flows through the conductor, heat is produced and electricity is lost. This is called the transmission and distribution loss. Now imagine carrying water through a long pipeline. If the pipeline has leakage, not all the water reaches the destination. Similarly, not all generated electrical energy reaches consumers. Some energy is lost due to some energy is lost due to a long transmission distance, then overloaded transmission line, then aging conductors, poor quality equipment, and transformer losses. So this losses reduces the overall efficiency of the power system. Utilities must generate more electricity than consumers actually require. Naturally, this increases the cost of electricity. This is one of the major reasons why improving grid efficiency is so important. Now suppose your college requires 100 units of electricity. Because of transmission losses, the generating station may actually have to produce around 1052 to 110 units. Those additional units are simply lost during transmission. Ultimately, someone has to pay for those losses. That cost is indirectly borne by consumers. Now let us understand another important technical issue, that is voltage regulation. Every electrical appliance is designed to operate at specified voltage. In India, in India, most household appliances are designed for approximately 230 volt. But what happens if the voltage becomes too low? Fans rotate slowly, then water pump fails to start, air conditioner consumes more current, motors may overheat. Now consider the opposite situation. Suppose the voltage suddenly increases significantly. Televisions, computers, mobile chargers, and LED lights may get damaged. Therefore, maintaining a constant voltage is extremely important. Unfortunately, the conventional grid cannot always maintain stable voltage. Whenever load increases suddenly, voltage drops. Whenever load decreases, voltage rises. This continuous variation is called poor voltage regulation. Smart grid technology continuously monitors voltage using intelligent sensors and automatically controls over voltages within acceptable limits. So students, have you ever noticed tube becoming dim during summer evening? Why does this happen? Because electricity demand becomes very high. Large currents flow through distribution lines, causing voltage drop. This is an everyday example of poor voltage regulation. Now look at the waveform shown in the slide. Ideally, the voltage waveform supplied by the utility should be a perfect sine wave. However, in practice, many disturbances occurs. These disturbances are collectively known as the power quality problem. Some important power quality problems are voltage sag, voltage swell, harmonics, flickers, frequency variations. Let us understand them one by one. So, a voltage sag is a temporary reduction in voltage. Suppose a large induction motor starts In factory, it draws a very high starting current. Because of this, voltage temporarily falls. The temporary reduction is called voltage sag. A voltage swell is exactly the opposite. Voltage temporarily increases above its normal value. Next comes harmonics. Nowadays, many electronic devices such as laptops, LED lights, mobile chargers, variable frequency drives, and UPS system use the power electronic converter. These devices distort the normal sine wave. Such waveform distortion is called harmonics. Another problem is flicker. Have you ever seen lights continuously becoming brighter and dimmer? That is flicker. Finally, frequency variations occurs whenever generation and load becomes unbalanced. Poor quality is extremely important for industries. Imagine a semiconductor manufacturing plant. Even a small voltage disturbance can stop the entire production line. Hospitals, data centers, and communication systems also require high quality power. Now, now let us discuss perhaps the most familiar problem, that is power outages. Everyone, everyone of has experienced power failures. But have you ever wondered why they occur? Power interruptions can occur because of transmission line faults, then transformer failures, lightning, then heavy rainfall, cyclones, tree branches touching conductors, animal contact, equipment failure, overloading. Once a fault occurs, the conventional grid usually cannot isolate it automatically. Maintenance personnel first identify the fault, then they travel to the location. After inspection, repair works begin. Only after completion of repairs, electricity is restored. So, this entire process is mostly manual. Therefore, outage duration becomes longer. In smart grid, fault detection, then isolation, and restorations are performed automatically, which significantly reduces the duration of these outages. Then the final technical drawback is aging equipment. So many transformers, substations, circuit breakers, and transmission towers currently operating in India were installed several decades ago. Like every machine, electrical equipment also ages. Insulation weakness then weakens, mechanical wear increases, efficiency decreases, maintenance requirement becomes higher, then failure probability increases. So think about a 20-year-old motorcycle. Even it is working, it requires frequent servicing. Similarly, old transformers and substations requires continuous maintenance. Replacing the entire electrical infrastructure requires enormous investment. Therefore, many utilities continue that using aging equipment, which ultimately affects the reliability.